Dynamic Matrix Control DMC, model-based optimization for complex multivariable systems, applying predictive control to resolve high-interaction constraint-driven processes. Dynamic Matrix Control DMC is a modern control strategy developed to address the limitations of classical PID-based methods in large, highly interactive multivariable processes. Unlike traditional feedback control, DMC uses empirical models of process dynamics to forecast future outputs and calculate optimal control moves. It is particularly effective in environments with many inputs and outputs, tight constraints, and the need for economically optimized performance. When to consider DMC? DMC is most applicable in industrial settings where multiple manipulated variables are present. Classical control techniques struggle with more than a few loops. DMC is specifically designed for systems with numerous manipulated and controlled variables, managing their interdependence systematically. Strong interaction between loops exists. When loop interaction is too severe for tuning, loop assignment, or decoupling to manage effectively, DMC can handle the multivariable nature by modeling and neutralizing cross-coupling effects. Constraints must be enforced. Most industrial processes have physical, safety, or quality constraints on variables, e.g., pressure limits, flow bounds. DMC incorporates these directly into its optimization routine, ensuring that setpoint tracking never violates process or equipment limits. Steady state and economic optimization is required. DMC includes a built-in linear programming optimizer that pushes process performance toward defined economic targets, e.g., maximizing yield or minimizing energy use, while maintaining stability and constraint adherence. The process is slow. DMC operates on a finite control interval, often 1 to 5 minutes, making it best suited for slower processes such as distillation, reactor temperature control, blending, and energy balance systems. Core concepts of DMC. Empirical model foundation. DMC builds its control strategy on a model of the process, derived from plant tests or historical data. This model predicts how the process will respond to control actions rather than reacting to current deviations alone. Prediction horizon and control horizon. Instead of calculating one control move, DMC forecasts multiple steps ahead, calculating a sequence of future inputs to minimize predicted deviations from the desired trajectory. First move implementation. Although multiple control moves are calculated, only the first is applied. The entire sequence is recalculated at the next interval, incorporating the latest measurements. This makes DMC inherently adaptive. Inclusion of process constraints. DMC considers hard limits on variables directly during optimization, ensuring control actions are both aggressive and safe. This contrasts with PID controllers, which typically require external override logic. Unified handling of disturbances and setpoint changes. By continuously solving an optimization problem, DMC naturally manages both regulatory, disturbance rejection, and tracking, setpoint change objectives. Advantages of using DMC. Handles large, complex control problems. Scales effectively to dozens of inputs and outputs, making it suitable for entire unit operations or even plant-wide coordination. Integrates constraint management seamlessly. Keeps all variables within safe and operationally efficient bounds without separate logic or operator intervention. Improves economic performance. Can drive the process toward optimal operating points based on cost, quality, or throughput objectives. Reduces interaction without decouplers. Eliminates the need for manual decoupling by inherently coordinating multivariable dynamics. Operator confidence through prediction visualization. Operators can view predicted trajectories of process variables and control actions, improving situational awareness and trust in automation. Limitations and requirements. Requires high-quality dynamic models. The success of DMC depends on the accuracy of the underlying process model. A poor model results in degraded control and suboptimal decisions. Needs reliable digital infrastructure. DMC must be implemented on modern DCS platforms with reliable data collection, signal validation, and communication paths. Poor instrumentation or unstable measurements compromise performance. Complex implementation. Unlike PID controllers, DMC requires extensive upfront effort, including process testing, model identification, simulation, and operator training. Not suited for very fast processes. Due to its time-based predictive nature and computational overhead, DMC is typically unsuitable for rapid loops like compressor surge control or ultra-fast pressure loops. Best fit process types: refinery distillation towers, reactor temperature and composition control, blending and ratio control across multiple streams, energy management in furnaces or boilers, plant-wide optimization with coordinated constraints. Conclusion: dynamic matrix control is a powerful and scalable solution for multivariable process control where traditional methods fall short. It excels in environments with complex loop interactions, strict constraints, and high performance demands. When implemented with a robust model and integrated with a reliable control infrastructure, DMC transforms reactive automation into a proactive, predictive, and economically optimized control strategy. All the files uploaded by the user have been fully loaded. Searching won't provide additional information. Dead time only processes, evaluating control challenges and dynamic impacts, understanding the delayed nature of pure transport lag systems, evaluating the properties of dead time only processes. In process control, dead time is defined as the time interval between the moment an input change is applied and the first detectable response in the output. It represents a total lack of observable effect, despite an ongoing internal change, and is also known as transport lag, pure delay, or distance velocity lag. Dead time is not just a nuisance. It is the primary contributor to process instability and oscillation. Any control loop containing significant dead time will inherently be more difficult to tune and stabilize, particularly when fast responses are required. The ability to recognize, measure, and where possible, minimize dead time is central to effective process design and control. Defining characteristics of dead time processes. No immediate response to input change. Dead time only processes show a flat output line for a fixed time period after the input step. There is no output change during this delay period. Inherently oscillatory behavior in feedback loops. Because there's no feedback during the dead time, controllers operate blind, which increases the risk of overcorrection and loop cycling. Common in physical transport systems. Examples include conveyor belts, material transport delay, pipelines, fluid travel delay, or thermal systems where heat must move through solid media. Dead time is additive. Both process and instrumentation contribute to total dead time. Minimizing it in either domain improves control response. Real-world examples. 1. Conveyor belt example. Material released at a valve takes a specific time to reach the weighing element downstream. The time delay is purely a function of belt speed and length. 2. Pipeline or thermal system example. Injection of diluent oil into a pipe alters viscosity at a measurement point downstream after a travel delay. This delay is purely geometric and fluid velocity dependent. Key properties of dead time. Steady state gain K. For a pure dead time process, the steady state gain is constant and equals 1 if input and output units are matched. It reflects the proportional change in output once the dead time elapses. No dynamic attenuation. Gain magnitude equals 1. The process does not change the magnitude of the input signal, only delays it. Pure phase lag. Dead time introduces a phase shift that increases with frequency. Specifically, the phase lag is directly proportional to both the dead time and the input signal's frequency. Phase shift due to dead time. The phase lag introduced by dead time is always negative and grows linearly with signal frequency. This is what causes oscillations in control systems. It slows down corrective action timing relative to the system's needs. In mathematical terms, for a given frequency, the output lags the input by an angle directly proportional to the dead time. Implications for control strategy. Dead time only systems are difficult to control alone. Since there's no immediate output to guide corrective actions, feedback controllers must rely on prediction or estimation. Techniques like Smith predictors or model-based control become essential. Controller must be slower than the dead time. The controller's speed should not exceed the dead time period. Rapid control actions can cause instability due to overreaction during the delay window. Design should aim to minimize dead time. Wherever possible, sensors and control points should be physically repositioned to reduce transport lag. This may include moving sensors closer to actuators or redesigning process geometry. Summary. Dead time only processes represent the most challenging class of systems for traditional feedback control. Their defining feature is a delayed response that decouples cause from effect over time. This complicates both manual operation and automatic control. Although true dead time only processes are rare, understanding their behavior is essential because real world processes often exhibit dead time as a significant component of their overall dynamics. Proper identification, modeling, and compensation for dead time are key to successful process control design. Capacity only processes, evaluating storage behavior and system response. Understanding how mass or energy storage governs process dynamics. Evaluating the properties of capacity-only process. A capacity-only process is one in which the primary dynamic feature is its ability to store mass, energy, or information without any significant transport delay or dead time. These processes are typically modeled as idealized systems that respond to input changes by gradually accumulating the effect over time. Their key feature is lag or inertia, not delay. Capacity processes are prevalent in industrial systems such as tanks, thermal masses, or electrical charge accumulators. They determine how fast a system can respond to disturbances and how much it resists change. Core characteristics of capacity-only processes. No transport delay. The process begins to respond immediately to input changes, but the response is gradual due to the inherent storage behavior. Dynamic lag without phase isolation. Output lags behind the input, not because of delay, but due to the gradual accumulation governed by the system's size and resistance. Capacity determines process inertia. Larger capacities store more energy or mass and exhibit slower response. Smaller capacities respond faster but are more sensitive to disturbances. Examples of capacity in process systems. 1. Level tank, mass storage. A tank that accumulates liquid. If inflow increases while outflow remains constant, the level rises over time. The rate of rise is inversely related to the tank's volume. 2. Furnace or oven, energy storage. A heated brick structure stores thermal energy. A change in burner setting causes the temperature to change slowly as energy is absorbed or released. 3. Electrical capacitor, charge storage. Voltage across a capacitor changes over time as it stores or discharges electrical energy, analogous to fluid level in a tank. Key dynamic types of capacity. 1. Non-self-regulating NSR or integrating capacity. Output continuously ramps. If the net input is non-zero, the output will continue to increase or decrease indefinitely until bounded by physical constraints, e.g., tank overflow. No natural equilibrium. The system does not reach a steady state unless inflow equals outflow. Without control, it will drift. Step input, ramp output. A step change in input produces a continuous ramp in the output, e.g., level rising at a constant rate. Typical in constant load systems. For example, a tank with constant outflow and variable inflow exhibits NSR behavior. 2. Self-regulating SR or first-order lag capacity. Output stabilizes naturally. The system has internal mechanisms like a level-dependent outflow that restore equilibrium after a disturbance. Step input, exponential response. A step change results in a gradually settling output that asymptotically reaches a new steady-state value. Built-in feedback mechanism. As the level increases, the outflow increases too, leading the system to balance without external control. Performance indicators for capacity systems. Time constant, Ta, a key parameter defining how quickly a system responds. It is the time required for the output to reach 63.2% of its final value following a step input. System gain. In SR processes, the steady-state gain is finite and measurable. In NSR systems, gain is undefined because output never stabilizes. Phase shift and frequency behavior. NSR systems exhibit a constant 90-degree phase lag. SR systems vary in phase shift from 0 degrees to minus 90 degrees depending on input frequency. Control implications. NSR processes require integral action. These systems accumulate error indefinitely unless integral control is used to stop drift. SR processes respond well to PI or PID. Their self-regulating nature makes them suitable for standard tuning practices with proportional and integral action. Capacity size drives controller aggressiveness. Small capacities allow for tighter, faster control, but increased sensitivity to noise and disturbances. Summary: capacity-only processes represent lag-dominated systems where dynamic behavior is defined by storage, not delay. They are found across all domains of process engineering, from liquid tanks and heat exchangers to power supplies and charge circuits. Whether self-regulating or integrating, understanding their response characteristics is essential to selecting appropriate control strategies. In real systems, most processes include both capacity and dead time, making these idealized models foundational for accurate process modeling and robust control design. Evaluating the properties of real processes, integrating dead time and capacity for practical control models. Understanding the combined dynamics of multi-capacity, dead time influenced systems. Evaluating the properties of real processes. In industrial automation, idealized models like pure dead time or capacity-only processes are useful for analysis but rarely represent actual plant behavior. Real processes typically exhibit a blend of dead time and multiple capacities, with complex internal interactions. Accurately evaluating these combined dynamics is critical for selecting and tuning control strategies that perform reliably under varying conditions. Characteristics of real processes. Combined dead time and capacity. Most processes exhibit both transport delay and storage behavior. For example, fluid must travel through pipes, dead time, before filling a tank, capacity. Multiple capacities in series or parallel, rather than a single isolated tank or heat mass, real systems involve multiple interacting or non-interacting capacities, each contributing to the overall process response. Effective time constants and dead time. The observable system behavior can be described by effective values that aggregate the contribution of all internal capacities and delays. Types of capacity interactions. 1. Interacting capacities, mutual influence. Changes in one capacity affect others. For instance, in a cascade of heat exchangers or tanks, downstream behavior can influence upstream dynamics. Complex dynamics. These systems do not settle independently. They create coupled responses that are harder to predict and control. Examples: exothermic reactor sections with multiple thermal zones, interconnected tanks with hydraulic back pressure, electrical circuits with mutual inductance. Not 2. Non-interacting capacities. Independent response. Each capacity element behaves in isolation from those upstream. The response of one does not alter the dynamics of the others. Simpler to model, non-interacting systems are more predictable and can be represented as a series of independent first-order lags. Examples: serial tanks with high resistance flow separation, isolated instrumentation elements with buffering amplifiers, combined effects in real processes, dead time from cascaded capacities. When multiple capacities are in series, especially non-interacting, the overall process begins to resemble a dead time capacity system. The more stages involved, the more the system exhibits apparent delay before response. Interacting capacities distort lag shapes. In systems with interaction, the time domain response deviates from a clean exponential curve. Responses become multimodal, requiring second order or higher modeling. Effective dead time increases with complexity. Even if no physical transport delay exists, the presence of several slow reacting capacities can simulate dead time behavior, introducing phase lag and reducing responsiveness. Key observations in real process behavior. Phase shift increases with process order. As more capacities are introduced, especially if interacting, the cumulative phase shift increases, making control loops harder to stabilize. Dead time to capacity ratio matters. Systems with high dead time relative to their capacity are difficult to control. Conversely, processes with short dead time and high capacity are more forgiving. Real processes often resemble dead time dominant models. Especially in systems with 3 or more serial capacities, the behavior approaches that of a process with pure dead time plus dominant lag, justifying simplifications for control purposes. Implications for control strategy. Model reduction techniques apply. Complex real systems are often reduced to first-order plus dead time (FOPDT) models for controller tuning, providing a usable approximation of true dynamics. Need for predictive or adaptive control. In processes with significant interaction or long dead time, conventional PID control may underperform. Techniques like dynamic matrix control DMC or adaptive tuning become essential. System identification must capture both lag and delay. Testing and modeling should account for both capacity driven lags and dead time elements to yield useful control strategies. Summary: real industrial processes rarely conform to idealized models. They exhibit multiple capacities, transport delays, and dynamic interactions that complicate control. Understanding how these elements combine into observable behavior, especially how they can simulate or amplify dead time, is vital for building robust, responsive, and stable automation systems. By approximating real processes using effective time constants and dominant dead time, engineers can apply scalable control methods while accounting for the inherent complexity of physical systems.